Try to imagine a world without numbers. It's not easy. Numbers are everywhere. They are part of a universal language. Number systems were in use thousands of years ago in ancient Egypt and Babylonia. Egyptians used pictographs, or symbols, to represent different amounts. Later, the Romans developed a number system using letters from their alphabet. These are called Roman numerals. The Hindu-Arabic numeral system that originated in ancient India is the system people use today throughout the world. This system uses 10 symbols for quantities from 0 to 9 and combines them to represent virtually any quantity. The location of a written numeral signifies its value as a power of 10. A place farthest to the right in a whole number is the ones place. The next one to the left is the tens place, followed by the hundreds place, and so on. A decimal point allows the inclusion of fractional values. This universal system has been a tool contributing to all kinds of discoveries. Look at physics and astronomy. Galileo used mathematics to make important advances in our understanding of gravity and motion, as did Isaac Newton. And where would the world's businesses be without a way to calculate financial transactions? It's all in the numbers. The types of numbers we choose are determined by how we intend to use them. Take a look. Numbers are essential in modern life. We use different types of numbers for different purposes. The dates on this calendar are natural numbers. Natural numbers, forming one of the most basic sets, are the counting numbers. The number 1 followed by 2, 3, 4, 5, and so on. We use them for just that, counting things. For any natural number, there's always a greater one. Just add 1. Include 0 in the set, and it becomes the set of whole numbers. You need whole numbers when you need to know when you have none of what you're counting. Integers are all whole numbers and their negatives. You need the negatives if you want to account for how much less of something you have than you need or expect, such as 1 less serving of food than the number of people. For integers, not only can you always find a greater one than any you choose, you also can always find a lesser one. Just subtract 1. So what about the numbers in between, like fractions or decimals? They've got plenty of uses. When it comes to baking, the ultimate sweet treat, donuts are often on the top of the list. And none are more popular than the classic glazed. When making the perfect glaze, culinary experts use rational numbers to make sure they have the correct ratio of ingredients. The ratio of milk to sugar is 1 to 8. 1 part milk to every 8 parts powdered sugar. You can write this as the rational number 1 over 8. A rational number is any number that can be expressed as a ratio of integers, a fraction in which the numerator and denominator are both integers. For example, 1/2 is a rational number, so is 2/3, 5/8, 7/16, but the denominator can never be 0. You can also say that any integer is a rational number because you can think of it as a ratio of integers, itself over 1. 4 can be written as 4 over 1, or as 8 over 2, or even as 64 over 16. There are an infinite number of ways to write any rational number. Decimals that can be converted to fractions are rational numbers too, such as 1.75, which is the same as 7 over 4. For rational numbers, as for integers, you can always find greater or lesser ones than any number you choose. In addition, you can always find a rational number between any two you choose. Just take their average. If you think about it, it's quite rational. With a maximum speed of 2,193 miles per hour, the SR-71 Blackbird is one of the fastest jet fighters on Earth. It could fly you from Washington, D.C. to Los Angeles in barely more than 1 hour. It's ordinarily more than a 5-hour flight on a conventional plane. For the blackbird to fly effectively and safely at speeds 3 times that of sound, its design and construction are critically important. Numbers play important roles in the aircraft's design and dimensions. To fit equipment, measure arc lengths, or make many other calculations, engineers often use a number called pi. Pi is the ratio of the circumference of a circle to its diameter. This ratio is approximately 3.14, and it stays constant no matter the size of the circle. Pi is an example of an irrational number. That's because even though it's a ratio of one length, the circumference of a circle, to another, the circle's diameter, it cannot be expressed as a ratio or fraction of 2 integers. It has no exact decimal equivalent. If we were to try to write out all its decimal digits, we would be writing forever, and the sequence of digits would never get to a continuously repeating pattern. Irrational numbers are numbers that cannot be written as the ratio of 2 integers, but they can be considered to have a place along a number line. The square root of 2 is another irrational number, near 1.41 on a number line. The combined set of all irrational and rational numbers is the set of real numbers. Real numbers include all integers, all fractions or decimal numbers in between them, and all irrational numbers as well. Interestingly, between any 2 rational numbers, you can always find an irrational number and another rational number. And between any 2 irrational numbers, the same is true. As you can see, these sets of numbers are never ending, not only going greater and lesser, but going in between them as well. Electricity is used nearly everywhere in the modern world. And for most of us, it would be hard to live without. But how does it work? Electricity is movement of electrons, typically in a circuit through wires and other components. Electron flow is related to magnetic fields. To help understand electricity and magnetism, scientists use square roots of negative numbers. Any number squared is positive, so a negative number cannot have a square root. But mathematicians play around with all sorts of ideas and have invented a system in which it is possible to have negative squares, using the letter I to represent the square root of -1. That is, I squared is -1. We call the numbers imaginary because they do not correspond to the more ordinary quantities we are familiar with, such as lengths of things, ratios, or locations on lines. And they don't exist in the commonly used number sets, real numbers, rational numbers, and integers. It turns out that such a seemingly strange system can be useful. Here's one simple example of how it works. To find the square root of -9, you could express it like this. It's the square root of the quantity 9 times -1. This becomes the square root of 9 times the square root of -1. Substituting I for the square root of -1, you get the imaginary number 3i. You can't represent an imaginary number on an ordinary number line, but you can represent it on a plane. You can graph an imaginary number using the vertical axis of a coordinate plane. When we do this, we refer to the coordinate plane as the complex plane. The horizontal axis of the complex plane represents the real number part of what's referred to as a complex number, a real number added to a multiple of I. So complex numbers have 2 parts, a real number, which can be represented as A, and an imaginary number, a multiple of I, which can be represented as BI. The standard format for complex numbers is A plus BI. 7 plus 0.4i is an example of a complex number. A real number, 7, plus a pure imaginary number, 0.4i. Notice one more thing. The distance of a number on a number line from 0 tells how far its value is from 0, how great or low the number is. You can tell how far an imaginary number is from 0, how great it is, by how far its graphed point is from the origin of the coordinate system, which represents 0, 0 plus 0i. You won't use complex or imaginary numbers to figure out how much your next movie ticket will cost, But for some problems in chemistry, engineering, and technology, these numbers are used to allow simpler calculations for analyzing complex systems.